So we're starting the second half of Unit 9 here, which is the Electromagnetic Induction piece, Chapter 25. So we're going to talk about electromagnetic induction, Faraday's Law, and kind of how that relates to things like generators, alternating currents, power production, self-induction, transmission, field induction. Something called Lenzs Law goes along with this too. Both Michael Faraday and Henry learned of this idea called electromagnetic induction. So basically we can induce a voltage by changing the magnetic field strength within a coil. So I made a coil of wire, and I actually move a permanent magnet in that coil of wire. Okay? By doing that, I can induce a current in the coil. All right, so in the last half of the chapter or unit, we've looked at the idea if I put a current in that coil, I can make a magnet. Now I'm saying if I put a magnet near the coil, I can make a current. All right, and that induced voltage can be increased by increasing the number of loops, okay, or how fast we move the magnet. So if I move the magnet faster, I get a greater voltage. If I move it slow, I might not get any voltage at all. All right, the voltage can be basically induced by either moving the magnet near the coil or moving the coil near the magnet. Okay, in either case, the magnetic field through that coil is moving. The magnetic field is changing that's going through that coil. So when the magnet kind of gets plunged into the coil, you know, if I've got twice as many coils, I'm going to get twice as much voltage. If I get 3 times as many coils, I'm going to get 3 times as much voltage, okay, as I'm moving it in and out of the coils. So this idea of moving in and out deals with 2 kind of pieces. One, the magnetic field that I'm actually moving, and 2, the area of the coil, like the surface area of the coil, you know, or that cross-sectional area of the coil. And it brings us to the idea of magnetic flux. And what magnetic flux is, which is going to be represented by phi, so it looks like a theta but with an I with a circle instead, that's phi. It's B, the magnetic field, times A, the area of that coil, times the cosine of theta. Okay? So when they're perfectly perpendicular, like in B, I don't get any flux through the coil. But when they're parallel, the area and the magnetic fields, if they were changing, I get a flux through the coil. Okay? If they're at some angle, it's then the cosine of the angle. That's how much is going through the coil. And again, you can kind of see with the shaded in areas here, right? More of the shaded in is going through the coil here, less of it's going through here, none of it's going through here. Okay? So here perpendicular is bad, parallel is good. Theta is equal to 0. And then at some odd angle, I've got less than I have here. Now the unit we're going to have for flux is the Weber. So a capital W, lowercase b is what we use for Weber. And it's the same as a Tesla meter squared. Where Faraday comes around is Faraday figured out how much induced EMF or electromotive force comes out of changing that flux through the coil. Okay, so EMF or electromotive force is kind of like voltage, right? So that electric potential. So he found out that if you had this rate of change of flux, so basically the change in flux per unit time, times a certain number of loops, you had a certain EMF. All right, and there was a negative in there, which we're going to talk about why the negative's in there in a second. Okay, it's in this thing called self-induction. Okay, so basically the induced EMF, which we're using this kind of funny looking E for, is equal to negative N change in phi over change in time. Okay, and this whole piece together is known as the rate of magnetic flux. So Lenz's law. So Lenz's law basically stated that an induced current always flows in the direction that it opposes the change that caused it. And because of that, that's why we get that negative sign. So if I pushed in to the coil, the magnetic field that I create tries to push the magnet back out. It tries to repel the magnet, okay? So if you notice over here, if I put a north end in, the field that generates pushes a north end out. It tries to stop me from putting that in. It's a really cool demo you can do where you take a magnet and you drop it into like a copper tube. And because of this idea of self-induction with Lenz's law, the magnet actually falls slower than if I just dropped it without going through the tube because of this idea of self-induction. Now, if I pull it away, it wants to pull the magnet back in, so it would create like a self-magnet. So when I'm pushing it in, it's trying to repel. When I'm pulling it out, it's trying to attract it. All right, which is kind of an interesting thing to have happen. So at all times, it's always fighting because of the coil there with the self-induction piece. which is why the negative comes in. It's always opposite the motion. So basically, Faraday's law is stating that the induced voltage in a coil is proportional to the number of loops multiplied by the rate at which the magnetic field changes within those loops. Okay? And the amount of current produced, right, by the electromagnetic induction depends on two things: the resistance of the coil and that induced voltage, right, which makes sense. V equals IR. So we're only going to make as much current as the loop will allow us to. The resistance that you feel when pushing a piece of iron into a coil involves repulsion by the magnetic field you produce, the energy transfer between the iron and the coil, Newton's third law, the resistance to domain alignment in the magnet. And it's the repulsion by the magnet you induced, or produced, I should say. Again, because Lenzs Law tells you that if I push it in, the magnet I create is repelling me. But if I tried to pull it out, the magnet that I create is trying to attract me. Voltages that are induced in the wire require a change in magnetic field by the loop. It means I can either move the loop near the magnet, move a magnet near the loop, or change the current in a nearby loop. That's another way to do it. So I could have two loops instead of having an actual magnet. So imagine having one loop and then a charged loop. Some actual real-world applications of this are when you drive up to a traffic light. If you ever notice there's like scoured lines around traffic lights, there's actually a coil of wire that's charged up. And as you drive your car over it, you change the magnetic field. By changing that magnetic field, you trigger the light. Metal detectors, they use two coils. So basically there's a charged coil and an uncharged coil. And if you go over a piece of metal, it distorts those fields. And detecting those fields is how it detects if there's a piece of metal there. So the scanning strip in the back of your credit cards, again, it's the same idea. Or even like on old tape cassettes, the same idea. You're basically moving that piece of magnet through a coil, and it reads the information by going through the coil. Hard drives that are in the old school iPods before they get into solid states, or regular computer hard drives, all relying on Faraday's law to store data. The more voltage that's induced when a magnet is thrust into a coil is going to be because you did it more quickly, more slowly, either A or B, or neither A nor B. And it's going to be A, more quickly. So the quicker I can do it, the more voltage is going to be induced when the magnet is thrust into the coil. Not only is voltage induced when the magnet is thrust into a coil of wire, but something else is also induced. Current, energy, power, or none of the above. And it's current, because if you have voltage with a resistance, V equals IR, you have to have a current. Another real-world application, this is a generator. So generators work by putting a coil near a permanent magnet. And if you put a mechanical input to rotate that, to cause that change in flux, you're going to cause a current. Now, it produces an alternating current just because of the fact that you change the loop's direction as you go through it. So you end up with positive, negative, positive, negative as you're going back and forth through the current, okay, the way the loop happens to form. You can build a DC generator, but the most common way for it to form is the alternating voltage and current. Transformers, so how you actually charge up most of your devices, your computers, your iPods. You always have that little, I call it the wall wart, the plug that goes into the wall. That takes the primary source over here, this would be your AC that you plug into the wall, one coil, out to a secondary. All right, so in your case, you're taking 120 volts and you're stepping it down to, for a computer, probably 19 volts or 12 volts. Or if it's the case of your phone charger, you only step it down to 5 volts because you have a lot of coils here and a few coils here, so it helps to step down the voltage through the induction process. So, key thing to remember here about electromagnetic induction is a two-way street, because, again, Faraday's law states that an electric field is induced with any region of space in which a magnetic field is changing with time. But then there's also this other guy called Maxwell. He has his own equations, and he has one that states, as a counterpart to Faraday's law, that a magnetic field is induced in any region of space in which an electric field is changing with time, which we just kind of learned about, again, in the first part of the unit. But we didn't say it was Maxwell. We just said, hey, here it is. But Maxwell's the guy that has the law.